Hello and welcome to your third revision video. This one is on chemistry paper 3. It's the first topic and it's on states of matter and mixtures. If you want to do further revision on this, it's on page 112 to 118 of the Combined Science Revision Guide. So the first thing you need to know are the three states of matter, solid, liquid and gas. And you need to know how the particles are arranged in each one, how they move and how much energy they have. So starting with a solid, it's in a regular pattern, particles are very close together, and that means they're all in very nice neat rows. They vibrate on the spot and they have very little energy. Liquids have more energy, they move around each other, they're still very close together, but their position is now random because they're moving. Then a gas has the most energy, they move fast in all directions, and so they're far apart and they're randomly spaced. So you have to know how to identify these and draw them. If we want to change from one state to the other, we'll start with solid. Solid turning to a liquid is called melting. Now when that happens, you're giving them more energy, so they're changing from solid to liquid. If you give them more energy, they move more, and so their position becomes random. If you heat the liquid further, you give it even more energy, it will evaporate, and it would be evaporating, or you could say boiling. Giving it even more energy, it turns straight to a gas. If you go the other way and you cool them down, a gas to a liquid is condensing, and a liquid to a solid is freezing. There are two others you need to know. If a solid is heated and it can turn straight into a gas without going through the liquid phase, this is called sublimation. It goes straight from a solid to a gas, doesn't become a liquid. The opposite of that is called deposition. Straight from a gas back to a solid, doesn't turn to a liquid. In your revision guide, they refer to this as desublimation. So you can use either. Point is, on this side, we're cooling them down so they have less energy. And on this side, they're getting more energy. And that's what causes the change of state. At the bottom here, we've got some example melting points and boiling points for this substance, bromine. Now, melting point is the temperature at which below it will be a solid, above it will be a liquid. It's the temperature at which the solid would melt. The boiling point, below it's a liquid, that's the temperature that it boils at, so above that it becomes a gas. Now what they like to ask you is to predict the state of this substance at 25 degrees Celsius. Well, 25 is in between these two, so it would be a liquid. If it was less than the melting point, it would be a solid, and if it was more than the boiling point, it would be a gas. Okay. The next thing that you have to know about are pure substances versus mixtures. So a pure substance is got the same type of particle or molecule all the way through it. This might be hydrogen gas, and throughout your sort of sample of hydrogen gas, you've only got hydrogen molecules, and it's the same all the way through. That's if it's an element. You can also have pure compounds, such as water, which is H2O. You've only got that one type of molecule throughout your substance, and it's the same all the way through. A mixture, however, has got different molecules in it. So you might have some hydrogen, you might have some oxygen molecules, you might have some water molecules. You could also have some carbon dioxide molecules. So in my mixture, if I look at this part, I've got some carbon dioxide. If I look over here, I've got some hydrogen. So it's different, it's made up of different parts in different places, different particles, different types of elements. So you have to know specifically what pattern they make on a cooling curve or a heating curve, depending on which way it's going. So if you were shown a graph, or if you made a graph plotting the temperature over time, for a pure substance, you would get a very distinctive straight line. So the temperature would be high at first, and as it cools, it's going to go down. And then when it changes state, say it started as a liquid, it's now going to change state and become a solid, you would see a straight, flat line on your graph. This is where it's changing state. And this is your pure substance in red. The temperature stays the same or stays constant as it changes state. However, if you had a mixture, you wouldn't get this flat line. It might start at the same temperature, but it's going to make a sloping line on the graph when it changes state. The temperature's changing, and this is because all of these different particles in your mixture have a different melting point. So there are lots of different melting points. So they don't all melt at the same time. So this is our impure substance, or our mixture. The changing state has only got one melting point if it's pure. Okay, the next thing you need to know is how to separate mixtures. So you know how to identify them from a cooling curve. You now have to know how to separate them. So this process here is showing filtration. Now how this works is you get your filter paper and you put it in your funnel, and you've got a mixture of a solution with an insoluble solid. It will only work to separate out insoluble solids from solution. What happens is the solution can go through. It's small enough to pass through the filter paper. The insoluble particles will get stuck in that filter paper, and they form what's called a residue, and they are trapped in this filter paper. You can take the filter paper away, you can wash the residue, and you get whatever that insoluble solid was out of it. The solution with some solvent and some dissolved particles, some soluble particles, forms what's called the filtrate. If you then want to remove the soluble particles from this filtrate, you need to use crystallization, which is this process here. Now you put the solution containing your solvent and your soluble particles, and you put them into your evaporating basin. You have to heat them over a Bunsen burner, so step 1 is heat. Now the purpose of heating it over your Bunsen burner is to get some of the solvent to evaporate. You need to do that so that the solution becomes saturated. So you cannot dissolve any more salt in that. That's what saturated means. You can't get any more of the soluble particles in there. Then you would leave it. You would take it off the heat, turn this off, and you leave to evaporate on the side in a warm room. And it's called crystallization because crystals form. That soluble substance is left behind in the bottom and it forms crystals, and the solvent evaporates off. If you do this slowly, you will get large crystals. If you do it fast, you get small crystals. So filtration and crystallization for your insoluble and your soluble particles to separate them out. The next process you need to know is distillation. So here we have simple distillation. Now you might have a mixture of two substances with very different boiling points. I'm going to put BP for boiling point. So you've got seawater, so you've got water and you've got salt. Now as you heat it, the water evaporates because it has the lowest boiling point. Salt has such a high boiling point it won't boil. So we've got evaporation happening here of the water. So the water turns to a gas, it travels up out of the flask and it goes into this Liebig condenser. You can just call it a condenser. Now the water's a gas, but you want to collect it as a liquid. So into the Liebig condenser and around the outside of it flows cold water in, and it's going to go all around the outside of this tube, and then the water goes out. It keeps this really, really cold. So any gas then condenses. So your water, which had evaporated, turned to steam, a gas, moves into this condenser, cools down, and the gas condenses. Then you end up with your liquid water, which is called your distillate. So this is pure. There's no salt in here because the salt got left behind here. The salt did not evaporate. Now, if you had two solutions with very, very similar boiling points, such as ethanol and water, you need to use fractional distillation, which is what this one is. So, if you tried to do that here, both would boil off and you'd get an impure substance at the end. So you need this fractionating column, this long column here. Now what happens is you heat them and both of them boil, or they both evaporate, and they start to move up the fractionating column, which is full of these glass beads. Now your column is colder at the top, away from the heat, and hotter at the bottom. Now between ethanol and water, water boils at 100 degrees C, ethanol boils at 65 degrees C. Now as it moves up the column and gets colder and colder and colder, the water is going to condense and drip back down. So here we've got water condensing in the column and drips down back into the flask. Your water's going to stay here. It's too cold at the top for the water to remain a gas, but at the top, because ethanol has a lower boiling point, it will still be a gas. So it moves into the condenser. The condenser's cold enough to condense the ethanol. So the ethanol drips down the condenser into this flask. The ethanol is your distillate. And it's pure. There's no water in there. The water could not evaporate out of the column because it's too cold at the top. So even though they have quite similar boiling points, we end up with water over here and ethanol staying in here. So that's fractional distillation. You also have to know how paper chromatography works. Now this is used to separate dyes in ink. So what you have here is some chromatography paper. The chromatography paper is quite absorbent. At the bottom of your chromatography paper, you need a line and pencil. You need your pencil line. I know I just did it in pen, but you need the pencil line because it's insoluble. When you put it in the mixture at the bottom, the pencil line will not dissolve. On the pencil line, you place dots of soluble ink. So that will dissolve. In the bottom of this sort of flask or container, you have your solvent, your liquid that will dissolve those dots of ink. Now, that could be pen, and you could be using water as your solvent. Now, you dip the paper into the water, and the solvent, and the solvent will move up the paper. When it reaches the dots of ink, it will dissolve them, and it will carry the ink up the paper. So, step 1, place bottom of paper in the solvent. Do not let the solvent go as high up as the pencil line. If you do, the ink will dissolve and sort of go into this solvent down the bottom here. You want it to go up the paper. So you place the bottom of the paper in the solvent. The solvent is absorbed up the paper. It dissolves the ink, and the inks move up the paper as well. So here we've got our different inks or different dyes in our ink all moving up the paper, and as that happens they get separated out. The reason why they get separated is because the most soluble go higher up the paper. So this yellow dye is obviously more soluble than this red dye. The least soluble don't go so high, they go lower. And if it's not soluble at all, it will stay on this pencil line. So you separate your inks. Most soluble go highest. This purple line here is called the solvent front. So you leave that going, and the solvent got all the way up to here. It's how high the solvent got to. You have to put a lid on it to stop the solvent evaporating. So lid to stop solvent evaporating, because you might leave it for a while. You don't want all of this liquid to leave. Now you have to be able to do a mathematical calculation with this. You have to calculate the RF